Hi everyone. In this video, I will talk about plots that look like this. These are called phase diagrams. I'll tell you about what a triple point is, how to find the bowling point, and other information that we can get from these types of diagrams. These figures come from a textbook that I use. And why don't we talk about the first phase diagram? This is for carbon dioxide. Phase diagram for CO2. We normally encounter CO2 as a gas, but it does have the three distinct phases: solid, liquid, and vapor. Vapor, obviously, that's the same thing as gas. And does it make sense that vapor is in the bottom right? If we look at this region right here, we have what? We have low pressure, low P, and higher temperature relative to the other phases. Okay? A substance at very low pressure, at very high temperature, they tend to be gases. And the higher the temperature and the lower pressure, the more ideal the gas behaves. And we could use PV equals nRT. That's just a review. Now, it actually might be worth learning how to sketch a phase diagram. So why don't we do this from scratch? What if they tell you in a problem that your boundary lines are in certain places? Or we're going to call this a triple point. We'll look at that later. What if they tell you the triple point is at a certain temperature or pressure? Would you be able to construct a phase diagram? In general, you start all the way on the left, and you're going to hit what's called the triple point. Put a little curve there. That's usually what happens in most substances. And the first thing we're going to talk about is this triple point. See if I can make it green. Triple point. Actually, before we talk about the triple point, let me finish the rest of the diagram. This line here, the boundary between solid and liquid, S and L, make it a positive slope. Okay, a little slightly tilted to the right. And this line typically is curved, like this, between the liquid and the gas, G. Now, this point, this is an abrupt end. Oh, that's how you spell it. Abrupt end. That point is called the critical point. We'll define both the critical and the triple point right now. Okay, the triple point. Where do I put that? Let me put it right here. Equals. It's the only combination of T and P, temperature and pressure, where we get all phases in equilibrium. Let's say at which all phases are at, or maybe not are at, but can be. Let's say can be at equilibrium. Okay. What about the critical point? The critical point is even more strange. It marks the critical T and the critical P. But what does that mean? Critical T and P. Well, for the critical temperature, yikes, let me put it somewhere here. That is the temperature at which its gas phase cannot be liquefied. No matter how high the pressure. Interesting definition. What about the pressure, the critical pressure? This is the minimum pressure that must be applied to liquefy substance at a temperature. To liquefy substance at its critical temperature. So there is an abrupt end, and again, it marks the critical T and the critical P. Let me show you up here. Okay. Actually, above this point, let's say we'll mark it with this green area here. That is called a supercritical fluid. Oops. Let me give you a little information about that. Supercritical. It's still a fluid, but it has very unusual properties. And actually, that's where I'm going to stop. It's a fluid with unusual properties. I'm not going to get into it, but it has uses. So companies can decaffeinate coffee using supercritical CO2. What that means is that they got to get the temperature and the pressure high enough to be in this area right here, supercritical fluid area, and that's the fluid they use to actually decaffeinate coffee. Okay, is that all I want to say? Yeah. These red lines, these are called boundary lines. I might have mentioned that before. And actually, why don't we do this? If we're at 1 atmosphere, okay, that's normal atmospheric pressure. And we put a person right there. At 1 atmosphere, at very low temperatures, CO2 is a solid. But as that person walks, you notice that the boundary line that they cross is the solid gas boundary line. There's no liquid. So what we can say here is that from this diagram, what can we take from it? The first thing is solid CO2 or dry ice does not have a boiling point. At 1 atmosphere, at 1 atm, because it goes directly from solid to gas. Is this thing focusing every time I move? Let me change that real quick. Focus one more time. Okay. Solid CO2 does not have a boiling point at 1 atmosphere. It actually has a sublimation point, right? It has a, let's not even call it sublimation point, let's say sublimation temperature. And that is -78. Solid CO2 does exist at room temperature. That's why we have dry ice, and it will sublime if left out outside of the insulating container. One other thing that we could get from this diagram is that also, oh, I already mentioned that. Also at 1 atm, the sublimation temp equals negative 78 degrees C. So you hit the boundary line and you rappel down to look at the temperature. Negative 78. Okay. That is carbon dioxide. Water is very unusual. It has similar shapes, but let me show you water. Here it is. You see a difference between the phase diagram of CO2 and this is the phase diagram of H2O. Okay. We're going to try to extract as much information from this phase diagram of H2O. The solid liquid vapor areas are still very similar to what we saw with carbon dioxide. So side by side. Okay. But there are a couple of things that we can take from this diagram for H2O. And we're going to see some numbers that are very familiar to us. Let's start here again at 1 atm and start walking. This is atmospheric pressure. This is pressure that's typically at sea level. Okay. As you're walking across, we're at very low temperature, solid. This is ice. You know that ice melts. So we're going to come across and we're going to hit this point here, the boundary, right? Boundary between solid and liquid. Rappel down 0 degrees. So this is how you find your normal boiling point. Normal meaning at 1 atm, not boiling point, freezing point. You understand that the freezing point and the boiling point are identical. Freezing point equals, am I saying this right? Let me make sure I write it correctly. Freezing point equals melting point equals 0 degrees Celsius. Okay. Let's keep walking. We're in the liquid phase now. And we're going to hit this point right here. All right. That is the boiling point or condensation point. Boiling equals condensation, the points, not the process. So our boiling point is the same as the condensation point, and for water that's 100 degrees Celsius. Now water does have a critical point. It's just off the graph, and you could get supercritical water. Here is the, interesting, here's the triple point. The triple point we can read is at 0. It's very specific, 0.06 atm. Very low pressure, and 0.01 degrees Celsius. Again, that is the pressure and temperature combination at which, in this case, water can be in equilibrium in all three phases. Next, this is what makes water unusual. Let's look at 0.0, give me 1 second, 0.05 degrees C, very close to freezing. That is in between these two numbers here. If we start at very low pressure and we go up, okay, we're walking, and now we're walking up, or we're climbing up the 0.005 degrees Celsius line. We're going to go from gas, right, to solid as you raise the pressure. That makes sense. You're basically solidifying the gas by pressurizing it. But look what happens if you keep walking higher. And actually, we should give a pressure here. Oh my goodness. Actually, I'm not going to write it down. But we could read it off the graph where we hit the boundary line. But if we keep walking, we're in the solid realm, and then all of a sudden, at some pressure, we become liquefied. That is unusual. So at some pressure, you go from solid to liquid. That's weird. Pressurizing it, but we become more liquefied. We become liquid at some pressure when we hold the temperature steady. Do you remember your CO2 line here? There is no temperature at which you could go from solid to liquid as you increase the pressure. Once you get into the solid, you're going to stay in the solid, right? If you hold the temperature constant. So there is a vapor to solid transition for CO2 and for water, but now we have a solid to liquid transition that most substances don't have. Let me give you a couple of take-home points. Most substances have a solid liquid boundary that has a positive slope. Positive slope. Positive slope. Water has a negative slope. Water's boundary is negative. Solid liquid boundary has negative slope. What is the consequence of that? What is the consequence of us being able to pressurize solid and make it a liquid at a certain temperature? Of being able to go from solid to liquid by pressurizing. Okay, this is going to sound a little strange at first. This explains why ice floats. That is, not that ice floats is unusual, it's just that the solid form is less dense than the liquid form. That's unusual. When we're pressurizing solid, we are making it more dense and it becomes a liquid. That tells me that liquid is more dense. So solid is less dense and it floats. Liquid is more dense. Because for most substances, what is it? The solid is more dense. And it sinks. So just visually, we could figure out whether the solid is more dense or less dense, whether the solid will float or sink based on this boundary line being having a negative slope or a positive slope. If it is negative, we have this unusual case where we could pressurize into a liquid and the liquid is more dense. Liquid is more dense than solid. That is the unusual thing. Exclamation point. Liquid here is less dense. Solid is more dense than liquid in most cases. Okay, let me show you one more unusual phase diagram. And I put a couple of test-like questions, but I'm not going to answer it in this video. Okay. See if you can do this on your own. But this is the phase diagram of CO2. Above, oh, not CO2. Above is the phase diagram for carbon. And what's unusual here is you have 4 distinct phases. The 2 solid phases you could split up into a graphite phase and a diamond phase. And some questions that are possible when you're looking at this diagram is how many triple points are there? And what are the phases that can coexist at each triple point? Which has a higher density? Okay, we started to talk about density of water and how that's unusual. Not of water, but the density of ice, solid water. Which has a higher density in this case, graphite or diamond? And then I thought this was interesting. Synthetic diamond can be made from graphite. Using the phase diagram, how would you go about making diamond from graphite? Okay, so those are the types of questions that you are liable to see when you're given a phase diagram.